Hello everybody, Sean here from SMD Methods. You're very welcome into this video. What I'm going to do in this video is tackle a first order ordinary differential equation problem by means of finding a solution using a Runge Kutta fourth order, or the RK4 or classical Runge Kutta numerical method for solving it. The Runge Kutta methods are absolutely phenomenal approaches to these non-stiff initial value first order ordinary differential equations of the form where the function is equal to some input of the independent variable and the dependent or dependent variables. So the question I'm going to tackle comes from a Southern Regional College summer exam for the Numerical Methods for Engineers module on their Bachelor of Engineering top-up course. So the summer 2024 paper gave this problem in question 6, and I thought it'd be no harm in tackling it and see how we go on with it. So what I'll do is I'll put this into OneNote initially. Let's add a page in here, and let's just call this RK4. This comes from SRC summer exam, SRC. Let's put Numerical Methods for Engineers summer exam 2024 Q6, and let's paste that into there. So what's asked for here is to solve this first order ordinary differential equation using a step size of 0.2. So my t, I'm going to start with some t. I'm going to step forward by 0.2, and I'm going to see, can I calculate out what's going to be a new x value, because the dx with respect to the small step sizes, dt is equal to that. So I step forward by a step t, or dt, which is h. I should get a new x, and that's what I'm looking for. So it is an initial value problem. So what I'm told here is that the interval is from 0 to 1. My step size is 0.2, which means I have 5 iterations: 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, and finally 0.8 to 0.1. Starting off with at t is equal to 0, the x value I'm going to start off with is 1. Okay, so let's get going with this. So for RK4, it's an improvement on Euler's method, vast improvement on Euler's method, which is RK1. RK1 tends to vastly overestimate the next x values, and then especially as you march further and further forward in time, that error accumulates and the solutions tend to blow up. And that will particularly happen where you have chose a step size that you believe is adequately small enough such that it captures the main changes that happen in the function from one step to the next step, whilst not being too computationally expensive. But these methods really aren't meant for written solutions or writing out solutions, because the step sizes do need to be very, very small to solve them. So you are using MATLAB or Excel or some other sort of software-based solver. So what I'll do on this one here is we will use a written solution for the first iteration, the first step from t is equal to 0 up to t is equal to 0.2 to calculate an x value at t is equal to 0.2, just so that we are sure we understand the method. And then what I might do is just use that solution to start off the next iteration without going the whole way through the next iteration, because I want to keep the video reasonably long, appropriately short, in other words. So what I'll do is I'll solve it out to t is equal to 1 using MATLAB after we've worked out the first iteration. So incidentally, this question here, question 6, is a problem I believe that was taken from this book here, Numerical Methods for Engineers by Stephen Chapra, an absolutely brilliant book and full of fantastic examples such as this one. There's work solutions throughout the the book, and this one here I believe was in the problems at the end of the chapter on the Runge Kutta methods, which I believe was chapter 25. Don't quote me on that one, don't hold me to it, but I do tend to remember these things. I believe it was chapter 25. It was definitely in the section there on ordinary differential equations. But try chapter 25. If you come across a problem in it, or any other problem on Runge Kutta, and you're getting it tight, surely drop me a message over, and I'd be more than happy to look at it, or whatever. Just let me know. So the RK4 method for solving first order. So they have to be first order. I shouldn't even have to write first order, right? It's implicit in saying you're using RK4 that the equation is first order. First order ODEs, and specifically initial value problems. And we would really like them to be non-stiff, because if they are stiff, we would need a variable time step, but Runge Kutta uses a fixed time step for each iteration. Our time step is going to be 0.2. So if you are looking at stiffer sort of models, you might need a variable time step. You would be looking at the likes of the MATLAB ODE 45 solver, which is brilliant at it. I can't mind what the name of the method is that uses, but it's not Runge Kutta. It's not RK4. As I said, RK4 uses a constant time step solution. So the idea is that your solution at the next time step, if you like, xi plus 1, is equal to your solution at the current time step, obviously because you can't go to where you're going unless you are where you are first, plus an adjustment to that, either going up or down. And that adjustment is given by a slope multiplied by a run, right? So a slope multiplied by a step size effectively is going to give you a height adjustment, right? So then you can have a height plus a height will give you a new height. So the slope that we're using, there's a slope. It's a first order differential equation, which is itself a slope. But here, it's not just that slope. If it was just that slope, by the way, it would be Euler's method. It would be, you'd just be using this K1 value, which is that slope there. But I'm going to take the average of the Euler slope, which is just that function. I'm going to take weight up 2 of a K2 functional slope, a K3 functional slope, and a K1, K4, right? So I have 1, 2, 3, 4, 5, 6 functional or kind of augmented slopes, predicted slopes if you like, functional slopes, and divide by 6 gives me an average one. Slope multiplied by a step size or run gives me a height. That height plus that height gives me a new height. That's the idea on RK4. So again, Runge Kuttas are derived from the Taylor series expansion. So Taylor series expansion relies on derivative information at a current location, and you expand about that location. So given that the expansion isn't too far away, either forward or backward, or half forward and half back, leaving you central, your predictions tend to be pretty good. So the step size must be small. So even in this case here, we're only going from 0 to 0.1. A step size of 0.2 is still pretty big. So, but again, I'm assuming it's big because of the time constraint that would be in this exam for calculating all these. So I have x of I plus 1 is equal to that. So these K1, K2, K3s, and K4s, what are they? Well, K1 is equal to the function value, is equal to the function, which is the slope, dx dt. And I'm going to use the independent variable, the current one, and my current step, and the current x value here. So I'm using t and x because that is what this is, a function of t and x. K2 is also the function, and it uses the t, but it uses an adjustment, right? I'm going to take t, and I'm also going to take half a step forward. X, I'm going to take that at the half a step multiplied by the K1 slope from before it. K3 is the function itself. Take the same adjustment to my step or to my time where I'm evaluating that, and then my x, same format, but we adjustment. I'm going to use K2, the updated slope for K3, and then K4, right? It's a whole, right? So I'm taking 2 of these because I'm only taking half steps, taking 1 of them because I'm not taking a half step. K4 only gets 1, so I obviously don't take a half step. 2 halves make 1, so I only need 1 here and I don't take a half. It's going to be t plus h, x plus h multiplied by K3. So there again is going to be my height plus a step multiplied by slope. Step by slope is the height, plus that height gives me a new x or a new height. All right, so let's check this out then for iteration 1. That's not even iteration, it's going to be, I'm going to say step 1. Right? It's going to be step or chug forward, like step 1. So step 1, I'm going to march forward, this case in time, from t is equal to 0, which is my very initial time, by 1 step of size h. Let's move my over here, where h is equal to 0.2. Excuse me. So that I can calculate a value x at t is equal to 0.2. So the initial value said that at t is equal to 0, x was equal to 1. I want to find at t is equal to 0.2, x is equal to what? That's what I want to find. Right, so initial value, that there is x of 0 is equal to 1. Here, x of 0.2 is equal to who knows. This here is equal to x of I for this step. This here is always going to be the x of I plus 1, plus the step, 1 step. All right. So let's do that. So for me to calculate out x of I plus 1, I need x of I, which I have. It's 1, plus 1/6 of all these k's. I don't know what the k's are just yet, but I have a method to find the k's. So k1 is equal to the function of t and x. So my function is 1 plus 2t by the square root of x. K1 is equal to 1 plus 2 by t. So t for K1 is just my regular t, whatever my t is. What is my t here? Well, at this current step, t is equal to 0. 1 plus 2t multiplied by the square root of x. So for K1, I'm just using my regular plain old x, non-adjusted x value at this time step. X is equal to 1. So here what I'm going to have is K1 is equal to 1 plus 2 by 0. 2 by 0 is 0. 1 plus 0 is 1. 1 multiplied by the square root of 1. Well, the square root of 1 is 1. So 1 by 1 is 1. K1 is equal to 1. All right. Now, what about K2? K2 itself is equal to the function, but I need to adjust the t value because I need to add on half of a h, and I need to adjust the x value, which is half a h plus k. Let's try that. So it's equal to my function, which is 1 plus 2 times my t value. Right? So my t value in 2 is going to be my current t. Right? So let's just try to write this. It's going to be 0 plus 1/2 of my step size. 1/2 of my step size is 0.2. Right? So 1 plus 2t, there's t, multiplied by the square root of brave and long of x. Right? So the x value I need to use for k2 is given there. X plus 1/2 of h by k1. So my current x value is 1 plus 1/2 of h, which is 0.2, by k1, which is 1. That'll give me k2. Right, so let's see, can we simplify this in a wee bit? I'm going to have 1 plus, now what's in the bracket here? I'm going to have 2 times 0 plus 1/2 of 0.2. 1/2 of 0.2 is 0.1. Multiplied by the square root. Let's see what we got in here. Of 1 plus 1/2 of 0.2 by 0.1. So 1/2 of 0.2 is 0.1 by 1 is 0.1 plus 1, 1.1, which is equal to 0.2 by 0.1 is 0.2 plus 1 is 1.2. 1.2 by the square root of 1.1. You can say that k2 therefore is equal to, let's see if we go to maybe MATLAB, let's do 1.2 multiplied by the square root of 1.1, close brackets, is 1.2586. 1.2586. Box that off. K2 value. All right, K3 value. A wee bit. I'm going to keep K2 inside because K3 is very similar. It's identical same. In fact, the only thing that's different is going to be this last value here. In K2, that's a K1 value. In K3, it should be the K2 value. So K3 is equal to 1 plus 2 times the t value. The t value again is this up here, 0 plus 1/2 of the step size, 0.2. Boom, boom, multiplied by the square root, so slightly longer. It's going to be 1, it's my x value, plus 1/2 of the step size, 0.2, by my k2 value, which is 1.2586. So this K3 here, this first one, is going to be identical same to what we got in K2, which is going to evaluate down to 1.2. There's no difference, no adjustment, but this one does have the adjustment because we're multiplying by that. There's going to be 1 plus 1/2 of 0.2, which is 0.1. 0.1 times 1.2586 is 0.12586 plus 1 is 1.12586. Which is going to be then, actually leave out that bracket. Make sure we have that right. Half that's 0.1, multiplied by that is 0.125, plus 1 is 1.125. 1.12586. Therefore, K3 is equal to 12586. 12586. Let's get the square root of that answer. Multiply that then by multiply 1.12586 by 1.2. So I actually have to be careful with that because that's not actually correct. I need to multiply that by 0.1 and add 1. So I'm actually going to do the square root of 1.12586, which is my answer. Multiply then by 1.12586 square root multiplied by 1.2. It's 1.2733. 1.2733. Let's box that one off. That's K3. Okay, K4 is equal to the function 1 plus 2 times t, but the t value here is going to be my current t value plus a full step size plus 0.2 full step size multiplied by the square root of my current x value plus the step size itself, not the half the step size, but the full step size multiplied by K3, 1.2733. Right, so K4 is equal to, so that's 0.2, 0.4, it's going to be 1.4 times the square root of that there. So we're going to take a fifth of that plus 1.2733. So we're going to take the answer multiplied by 0.2 and then do the answer plus 1. That's 1.2547, and we want the square root of that answer is 1.1210. So I'll have the square root there actually, which is 1.2547, I think it was. Just double check that. 1.2547. So this is going to be then K4 is going to be equal to let me just take that out there again. Just to keep it the same, go for K4 is equal to, so I did the square root there of 1.2547 to get 1.1201. So then let's do the answer, and I'm going to multiply that there then by 1.4. We get 1.5682. All right, so there's K1 down to K4 found. Now I just need to put them back into the formula here. So just for convenience, speed, and consistency. Oh, I might have missed that 6, I did. Control C, Control V, and paste this down here. I'm going to return the 6 I missed and start plugging in values. So x of I plus 1 is equal to x of I, which is my current value of x at t is equal to 0, xi is equal to 1, given in the problem, plus 1/6 of, tidy that up, 1/6 of K1, I believe was 1. K2 is 1.2586. So I have 1 plus 2 times 1.2586 plus 2 times K3, which is 1.2733, plus the K4, 1.5682, all multiplied up by my step size 0.2. My x of I plus 1 is equal to 1 plus 1/6 of that quantity there. So let's see, can we maybe do this and bring that there, bring in a MATLAB. Let's get the log up there, see what we have, and see can I fit, I just about can. Let's go 1 plus 2 times 1.2586 plus 2 times 1.2733 plus 1.5682. That's 7.6320. 7.6320 multiplied of course by 0.2, which is my step size. So therefore x of I plus 1 is equal to 1 plus this adjustment. So I'm going to take my answer here I'm going to take divide by 6. That gives me an average K, 1.2720. And then I'm going to multiply that there by my step size to get an adjusted height, which is 2544. 2544. I add 1 onto that, which I should be able to do without MATLAB open to the left. X of I plus 1 is equal to 1.2544. So that's my solution at the next time step. So to formalize that, I had at t is equal to 0, x was equal to 1. This was my initial, write it out, initial value. Put in values, t can be considered initial, possibly. Right? And then I calculated at t is equal to 0.2, which is equal to time plus the time step. X is equal to 1.2544. So now what I could say is let's let xi equal to x of I plus 1. So at my, I now need to calculate from 0.2 up to 0.4. So where we had here, marching time from t is equal to 0 by step size that, right? I didn't put in step 2. I should have wrote in step 2, calculate k's, step 3, then calculate your new x value. But just again, for consistency, let's take this, Control C, select, let's put it in here, Control V. So can we set it onto a line? So this is going to be march forward in time, but this time from not t is equal to 0. We've done that. From t is equal to 0.2, which is not my initial time, it's now what is my current time, my I time, by one step of size h is equal to 0, so that I can calculate a value of x at t is equal to 0.4. Right? So what I'm doing is I'm using these two values here as my current ti and xi values. So we could then say, as we did before, k1 is equal to the function value now at t and x, which is equal to the function value at t being 0.2 and x being 1.2544. Plug them values in. K2 is equal to the function value at t plus 1/2 of h, x plus 1/2 of h multiplied by k1, which is equal to f of t is 0.2 plus 1/2 of the step size, 0.2, x plus 1/2 of the step size, 0.2 by k1, whatever you worked out when you calculated that up there, and so on. K3 is equal to f of t plus 1/2 of h, x plus 1/2 of h by k2, which is equal to f of 0.2 plus 1/2 of h, which is 0.2, plus x plus 1/2 of h, 0.2 by k2. And finally K4 uses K3, f is equal to t plus h, x plus h by k3, which is equal to the function of 0.2 plus 0.2, 0.2 plus 0.2 x. I don't know why I didn't put in. I should have actually did that. Give me 1 second, please, to see if I can write this. Write this, mean correct it, make it what it should be. That's obviously not a plus, that's a comma. My x value, don't need to write, I wrote in what my x is there, but my x value is 1.2544 plus that, 1.2544 plus that, 1.2544 plus my h value is 0.2 by K3. And then, of course, my x of I plus 1, which is going to be my x at 0.4, is going to be x of I, which is 1.2544 plus 1/6 of K1 by 2 times K2 plus 2 times K3 plus K4, all multiplied, quantity multiplied by my step size. X of I plus 1, so that there, of course, is at t is equal to 0.4 is equal to x of I, which in this case now is going to be 1.2544 plus 1/6 of my K1 plus 2K2 plus 2K3 plus K4 multiplied by h, which again is 0.2, and so on. And that's your new value there. That'll give me a new x I plus 1 at t is equal to 0.4, and then I'm back to this again. I go to 0.6. So, as I said, time is marching on. There's 32, no pun intended. There's 32 minutes going, so let's swap on in here to MATLAB and see, can we write out some sort of a function that'll calculate out the rest for us. Let's clear that out. Let's write in a new live script. Let's put in a wee bit of code or text to give it a title. So this is going to be RK4, and this is coming from Q6 of SRC, Southern Regional College, Numerical Methods for Engineers, Summer Exam 2024. And we'll come back on into this, and let's take a snap of what the function is. Let's come on into here, and this actually what I'll do is I'm going to put in a section break, put in a bit of text, and let's see, set up our computational space, computational domain, if you like. Right, so what we're going to write into here is my step size. H is going to be equal to 0.2. Let's comment that as a step size. Our t is going to be the domain over which we're solving. It starts at 0. We're going up by a step size, and we need to go all the way up to 1. So this is going to be our domain. Domain over which we will solve. And this is going to be time s. Right, there's our t. So our x is going to be our solutions. Right, so our x, let's make this up. Let's initialize this as a variable, make it as zeros. Put in one row, and column wise, let's go for the number of elements in t to state that for every t value we're going to have an x value. So they match up. So this is going to be a storage for x values at corresponding t values. All right. So likely position in meters maybe. Right. So h, t, x, we will also need to calculate out our k's, right? So we don't have to store these. I like to store them because it'll help us check back on our written based solution. So let's go for k is equal to, let's make this like this. Let's go for zeros, let's go for 4 rows, and again numl t. And what I'm going to say in this one here is that I'm going to have 4 rows. So first row is k1, second row is k2, third row is k3, fourth row is k4, and then the number of elements is t. So for every t value, we're going to have corresponding k's. So this is going to be same thing, storage for k values to solve RK4. Think there's, let me define my function. I'm going to save my function. I'm going to call it f is going to be equal to, I'll do this with a handle. I'm going to define it with a t, and I'm going to define it with a x, and that is given by 1 plus 2 times the t multiplied by the square root of the x. And this is going to be the function itself. Function to solve. I'll write it in as the ODE function to solve. First order ODE function to solve. Okay, that's that one. First order ODE function to solve. Let's put in a section break here. Let's put in a bit of text. Let's say, let's initialize, initial value definitions. I'm going to code that up. Our initial t, we're going to start with 0, so we're just going to keep it at that, but I'll just to formalize it, I'll say t, force value t should be equal to 0. It already is 0. See it there. My first x value, though, x1, has to be equal to 1. That's what the set is. So at the minute it's 0. Now I'm just going to set my first x value in that vector to be 1. Alright, let's section break this, put in a text, and let's solve RK4 in here. Go for code. Let's do it with a for loop. For I is equal to 1 all the way up to the number of elements in t. What I'm going to do is I'm going to solve my k's first. I'm going to say k, first row in the ith column. It's going to be equal to my function value. But what I'm going to do is I'm going to put in my t value, my first t value, and my x value. So it is the function evaluated at the current t and x values. There's no adjustment to be made on them. So I'm going to go for t of I, and also my x of I. They're the values I'm going to put in for that. Right. K2, this iteration, is going to be equal to, of course, the function. I'm going to go for t of I, but I need to adjust that. Plus, it's going to be 1/2, which is 0.5 times the step size. So I'm just going to put that t into its own bracket there, and then the x value itself, I'm going to take the x of I, and I'm going to add on 0.5 times h times the k1 value, k1 of I. That's it there. Semicolon. Now, k3 of I is identical same, except instead of using, let's change that 2 to 3, instead of using k1, I use k2, k3, and the k4, similar, except I'm not taking half of h, I'm taking a full h in both the independent and dependent variable adjustments, and indeed this will be k3. Now, last thing I want to do is I want to calculate out my new x value. So x of I plus 1, in this case, is going to be equal to my x of I plus the adjustment, which is 1/6 of the quantity, k1 of I plus 2 times k2 of I plus 2 times k3 of I plus k4 of I multiplied by my step size h. I should do that. X of I 1/6 of, let me see, k open bracket. Yeah, that looks pretty good. All right, let's go for it. I haven't commented these here, so hopefully by virtue of the fact that I've defined them as k's out here and x's here, it'll state what they are, or it'll make sense what they are. So I just ran that. Everything has seemed to have popped out okay here. Let's have a look at our x values. So 1.2544. So the x that we calculated by our hand calculations, 1.2544. So we have nice agreement there. And I can see that my x values are steadily rising. 2544, 1.6384, all the way up to 5.3823, which is, we're going one too many there, because obviously I've calculated the last xi plus 1. Let's double check our t's, make sure they're right. 0, 0.2, 0.4, 0.6, 0.81, lovely. And let's have a look at our k's. So there's k1, 2, 3, and 4. So let's just double check that. These should be right because our x's have been right. So I'm at a 1 and then a 1.2586, checking our hand calculations of a 1, 1.2586, and then we have 1.2733 and 1.5682, 1.2733, 1.5682. So everything looks hunky-dory there. So I'd like to assume that if we did calculate using the pen-based calculations into the 0.2 up to 0.4, we would have got correct answers as right, because we understand the process very well. So the last thing what is worth doing is just plotting it. Let's have a look at what the function looks like. So let's put in a section break in here, text. Let's look at plots, put in a code, put in a figure here for let's plot t versus x. We'll grid on that. We'll go for our x label to be, our x label is t. Let's just make it t. Seconds, who knows? And our y label, let's make that an x, which could be position. Let's go for meters. Let's see. Oh, and what we'll need to do, because our vectors are two different lengths, t is 1/6, x is 1/7. So what I'll do is I'll take one off that there. So I'll calculate one less x variable on that figure. Oh, this figure. Can't mind what the function there was for that one. Let's open this one. And so there we go. So there's our position is climbing exponentially against time. Time is running from 0 to 1. And there's our step size is 0.2, 0.4, 0.6, 0.81. And we see at 0.1, we're at our 1.2544, which is correct. All right, so that's our function there. We can add in a title here, put this as Q6 from SRC, Numerical Methods for Engineers, Summer Exam 2024. Subtitle that up as RK4, like so. All right. So there we are. So yeah, that's that. That's that there completed. Working through that. So marching it forward in time, it's just a repeating process. So as I said, these do lend themselves to MATLAB and to Excel, or as soon as you hit run, and provided there, of course, that your script and your code is right, that'll execute, in fractions of a second. It's so much faster, and in fact, what it actually let us do is that I can change my time step. Like even if I change the time step down to 0.01. Right, and I can run it. There's it finished already, and straight away, instead of running with all of them, the 5 time steps that I had, right, I'm now up to 100 time steps onto that there, like of a phenomenal amount of results out of that in a very quick or in a very quick time, in a very small interval of time. Everything is put together. So yeah, look, I hope that made sense. I tried to be as thorough at the sake of running this video very long, very thorough as possible. However, if there is any questions, of course, just drop me a comment back, or get in contact. Ask your question, and I've been more than happy to answer that. I do enjoy working through these things and talking about these methods. So another thing, if you want to hit subscribe on this one, every time I put up a new video here, whether it be on numerical methods, or whether it be on CFD, or whether it be on fluid dynamics, or whatever other sections, PLCs, that I do look at in the channel, you will get notifications for it. So if you are studying mechanical engineering and you do think that these videos could be of help, consider giving it the subscribe. Yeah, I'll keep putting these up so long as there's interest shown in them. So again, thanks very much for your time. I really appreciate you coming in and having a look at this, and I appreciate hearing any sort of comments, suggestions, variations, or any other views that you might have on what I've done here in this video, or what I might do in future videos. So thanks very much. Good luck.